Thank you, Simon, and thank you, Simon and Vincent, both of you, for the invitation and for the opportunity. As I said, actually perfect timing. So now the paper is actually out after years of work on this. I think the preprint was out for a year now. So I'm very happy to finally talk about the topic that is actually published. Before I go into the topic, maybe very briefly, because I had a brief look into the participants, and I think that maybe not everyone would know Wuppertal because in contrast to KAUST, we are actually in a center here with a lot of different cities bunched together. So typically everything comes together and people yeah, well, don't know every single one of them. So we are between Cologne, Dortmund, next to Düsseldorf, Essen, Bochum. So maybe you know this region somehow, at least one of the cities. And Wuppertal is one of these cities sitting this huge conglomerate. I think it's called the Metropoli region, which is actually rivals Berlin in terms of size, just has tons of different city names. So what Wuppertal is actually famous for is this nice suspension railway. So if you visit us, so this is our university campus, at least the main campus, and then we can of course together drive this one, which is always an attraction that we do basically with everyone visiting us to a group. So we are the group of electronic devices. So we are working for Professor Thomas Riedel, and we are focusing on all different kinds of electronic devices, mainly with relation to optics. So we like to build light emitting devices. We like to build lasers. We use a lot of technology. So we do a lot of atomic layer deposition. We have a huge activity on microscopy. And of course, we have the activities that I'm coming from. So that's the group of organic and hybrid photovoltaics that I'm now heading for 2 years now. And where I want to talk, and we are also hiring. So our group is currently hiring. So please have a look at our website. There will be a job posting very soon. Anyhow, I was coming here to take you on the trip of a firstly very frustrating and later on very satisfying journey. And I start out with the amount of co-authors that are on this paper, which gives you maybe a little bit of a glimpse of how many different aspects we were looking at. So the people that were with me on this path mainly was my former master student and now PhD student Timo Maschwitz and Dr. Lena Merton from University of Tübingen, who really walked this path, I think, for it was easy 3 years until we actually figured out what I'm about to present to you now. So what was the path about? So we wanted to understand, so I was a PhD student at the very beginning. I was building my perovskite solar cells, and I think everyone building perovskite solar cells knows that it can be a struggle because something changes and suddenly everything is different. And then you stand in front of your perovskite and everything is shit and you don't know why. So we got the idea, we're engineers, we like to have control over things. And we got the idea, okay, let's try to understand this. Like young and naive as we are, we thought, okay, let's go for nucleation, let's go for the stuff that is in literature. We typically, so this is nothing new here, obviously, like that we can do anti-solvent, gas quenching, vacuum quenching in order to increase the control that we have over the perovskite. That's something I think is well established in the community. And what we wanted to understand is if you can make it smooth, how can you make it large? So how can you make a small grain perovskite into a large grain perovskite? And if you look into literature, so like there's a lot of literature about nucleation, how the nuclei form in the precursor ink, and how then you reach to supercritical size. So actually this picture here in a little, probably maybe more beautiful way is written here in this paper from Journal American Science Society, which is pretty old. It's just a regular crystallization technique. Basically, you say you have seeds that grow, and eventually on these seeds you have additional material sitting on. And if you just apply this on the perovskite crystallization, you would basically say, okay, what I have to do is I have to make sure that I have a lot of small nuclei if I want to have small grains, because the small nuclei will grow until the next nucleus is there, and then it will stop. So that's basically, if we come from here, we have a small amount of nucleus, we have a large grains. If we have small nucleus, eventually we have a smooth layer of small grains. There is more papers pointing us in this direction. And again, like we just basically wanted to see them. And this was roughly what we were starting out with. So we're saying that at the beginning, we said we have like some precursors that are filled, that are basically lead complexes. Then we eventually, when we do the spin coating, we have some concentration going up, and eventually we will either have no additives, where we already know we have small grains. We would expect like a large amount of small complexes, and when we put the additives in there, we would have a small amount of large complexes ending up with this large grains with the additive and the small grains without the additive. So that's basically what we started out with. And then Timo went to the lab, and one straightforward way in order to make sure that your speed of nucleation should change is to basically just change the deposition technique. And I wouldn't believe him when he came to me first time telling me that all the grains are the same size. But we repeated this experiment, and it apparently, even though they looked very, very differently in terms of morphology, eventually, if he did the process parameters right, he was actually able to give me the same grain size, no matter if we would do drop casting, one-step deposition, gas quenching, or anti-solvent. If you look into literature, this might not be surprising, but if we think about the classic nucleation approach, this actually feels a little bit odd, because if we're talking about time scales, so here for the precursor to turn darkish takes like 30 seconds. In the drop casting method, we took like, especially with the MSO, it took minutes for the precursor to the solvent to eventually evaporate. So this somewhat confused us. And so we were wondering, okay, maybe stuff happens before. So maybe the drying is not the problem. Maybe stuff happens in the precursor ink. So there's a lot of work actually, and a lot of very, very good work on the things that are actually going on with the precursors. So we already know that the solvent will be forming complexes with the lead highlights. Possibly also with a methylammonium or the A side cation, but what you can actually nicely probe is the lead halide. There's like a huge amount of different complexes that can be there. And these complexes have been, well, in the next level of complexity, often taken as the root cause for why grains are large or small. And basically that these are the nuclei, and they define, okay, how many nuclei we have in the precursor, and then we spin coat them, dry them, and then they grow. This would explain why we got all the same grain size every single time. But we thought, okay, we should be able to see them, right? So the first thing that we did is we performed some UV-vis measurements. So this has been done by the group from Eva Unger before. So it's basically reproducing this stuff here. And one thing that actually looked quite nicely was that we, in the beginning, were able at lower concentrations, so the yellow curve here, we will basically be able to see like a very low amount of colloids. And then eventually, when we increased the concentration, we went from monomers to dimers to trimers of complexes sticking together. So this actually aligned quite well with the drying hypothesis, and that if you go up in during that you will start off with small colloids, and then you eventually develop into larger grains that will then form the perovskite grains that we all think about. Another way of probing this is actually having a look at the lead chemistry. So what we did here is we use lead NMR. So we basically used liquid NMR on the lead core. Here you can see the basically the ability to coordinate with the lead of the solvent. This actually this is a paper from Kai, and quite a while ago already, and we were basically he was classifying different solvents or different materials by the level of Lewis basicity as being solvents or additives, and this basically means that they interact with the lead core. We were able to see this with the lead NMR quite nicely. So until then, we were actually quite happy. So if you do this over concentration, and if you start out with different solvents, so you started off with DMF, DMSO, and NMP, and then if you increase the concentration, so if we go from the left side to the right side, we will see all of those, all of the signals, all of these lead NMRs approaching each other, which we interpret as basically a confirmation of what we've seen before. So like we start out with small complexes that have a lot of solvents around that do look more like, the complex actually. And the further we go towards this larger colloids, the more we go towards a solid state perovskite-like stuff or colloidish species that we have in the solution. And this actually fits quite nicely with the solid state NMR. So if you do a solid state NMR, you end up with 1423 ppm, which is the chemical shift in the NMR. And it's almost perfectly in the middle between there. So the asymptote, or the seeming asymptote that we have here, basically looks like it's passing through towards the solid state NMR. So far we're happy. Another technique that we used to probe this was simple conductivity. So basically we did an AC field. So we put two carbon electrodes, we applied an AC field, and then we had like a circulation pump, so just that we can change the concentration in this part here. And we just got the idea that if you have like a lot of small ions flying around in the precursor, this should give you high ion conductivity, and the other way around, if you have like these large complexes, this large multi-trimer, quadrimer, whatever it is, species flying around, that the charge to volume ratio is lower, and you would have lower conductivity. And straightforward said, this is the case. So the methylammonium iodide, so these are the empty signals here. This is a dissociated salt. So here, this is basically how we would expect the conductivity to go if we have a well dissociated, if we have no bundling together of the colloids. And then when we add lead iodide, so basically when we go from a salt solution into a perovskite precursor, we drop in conductivity, which means that we add material that should create more ions, but instead drops the conductivity, means we go from this case to this case. So we can confirm once again, we have larger things in the precursor that conduct ionic charges less good. So everything so far points there that when we go increasing in concentration, we have this buildup in this colloids, and we were very happy about this because now we are good to actually probing how we can use this, or how we could use this to increase the grain size and to explain why the grain size goes up. We chose, again, like from this nice graph from Camel, we chose the thiourea. This is an additive that we also used for the tandems, but we also used for, I don't know, 6 or 7 years already for the best devices that we are doing. We know that it actually brings us very large grains. We get very nice crystallinity, and indeed, in terms of efficiency, we actually get much better devices in direct comparison with and without the additive. Again, like the wide band gap, basically everything that we published in the past is with this additive. And then we decided, okay, let's look how this behaves in NMR. And this is where the frustration began. Because having a look at different solvents here, so you always see here the peak that we see in lead NMR. So basically see the environment of the lead. We put the additive in there. According to the Lewis base activity, it should have a huge tendency to coordinate with lead, and the lead didn't change. Not at all, no matter what we did. We did DMF NMP, we did NMP, DMSO, DMF, so solvents that are highly coordinating, less highly coordinating, mixtures of solvents, all of them gave us almost identical signals. And then we did the conductivity measurements, and the same results. So basically, it was impossible to disentangle what we got with and without the thiourea by one of these two methods, which made us a bit confused, because this was literally what we were thinking about, right? So like the whole hypothesis that we're talking about basically depended on that the amount of colloids, the size of colloids, and what we basically see depends on what happens in the solution. So far now, we don't see any correlation between the size of the colloids and the nature of the lead complexes and the increase of the crystal size in the end. And this, well, I told you this was a very frustrating. So you basically had the first year of our journey. So now basically Lena Merkel comes in because we got the idea, maybe we were wrong. Maybe we are looking at the wrong part of the process. And this is why we went away from the lead precursors and went back into the perovskite formation process by doing grazing incident wide angle X-ray scattering, which Lena Merton, who is actually able to do this in DESI, and she's able to do in situ studies. So we were with this one, we were actually able to probe the perovskite while it formed. And what we did is we did basically the same stuff that we did before. We have one sample without thiourea, one sample with thiourea. We've deposited it. In the end result, we get without thiourea a very randomly oriented perovskite with more grains. With thiourea, highly oriented. So this is what you see here in these more localized scattering patterns, that it's very well oriented. And then we probed what actually happens during the formation. Here you also see the setup. What we have is a gas quenching nozzle. So we didn't want to have the anti-solvent flying around there because it changes the atmosphere. We had an infrared heater. So we heated from the upside. And then we were basically having the X-rays hitting and looking at the and us looking at the parts at the same time. And the first thing that we did is we did the radial plot. So just having a look at what forms. And just having a look at this plot is actually very underwhelming because it looks exactly the same. So we know this from before, right? Being exactly the same, even though you don't expect it. This is something that we have before. So we took another way of looking at this kind of data, because we know in the end, we have maybe the same perovskite phase, but we have different orientations. So what we did is we probed along the radial axis here, and along the azimuthal axis. And this azimuthal axis basically gives you the orientation. So basically this point here versus this point here, or basically this point here versus this point here, gives us a measure of the orientation. So we can finally probe when during the perovskite deposition, we actually end up with larger and more well-oriented grains. And if we do this, we see something that at least surprised us quite a bit. Because when we started out with the perovskite spin coating, everything looked the same. When we did the gas quenching, basically doing the nucleation, basically doing what we think was super, super important, everything looked exactly the same. And I have to say that here already the perovskite forms. So these points here, these are actually the perovskite. We'll see this in the next slide. And then eventually just the moment when we started the annealing process, that's the moment when the grains started growing, and that's the part when they started orienting. So I put this in a little bit of a more direct representation. So in black, you see the perovskite. In red, you see the intermediate. So I think, so this is basically the thing that happens between a perovskite and the liquid phase. So you have like a solvent complex intermediate. And the interesting part is that already during the gas quenching, we have a significant amount of perovskite actually appearing. So we have not a pure intermediate. This is different for DMSO. So this is something that we see in DMF and NMP. But what is most surprising is that this perovskite that happens or that occurs until the annealing starts looks exactly the same in terms of orientation and in terms of basically every parameter. And then we put it on a hot plate and suddenly things start changing like crazy. Which basically led us to the point that focusing on nucleation was maybe a very bad idea. So basically our original hypothesis went into the rubbish dump. And we started looking for what the heck is happening there on an already formed perovskite when you put it on a hot plate with an additive inside. So this is like a little bit of a sketch of a working hypothesis. So you basically have your precursor, you have your concentration, during spin coating, the colloids grow, you will get these grains, these nucleus, they will grow, it will form your perovskite. But this already well-formed perovskite, the distinguishing between without the additive and with the additive, then happens the moment when you put it on the hot plate. And we asked, of course, ourselves, why? Because, well, I think we all can agree that if there's no solvent in them anymore, if the perovskite is already there, we cannot talk about nucleation anymore. So we had to come up with another hypothesis, another explanation for how this comes to pass. And lucky us, we ran into Olivier and Martin, who were studying perovskite coarsening for a while now already. And they looked at our data and said, hey, wait, this looks a lot like a coarsening. This looks, chemists know this as Oswald ripening. So it's basically the redistribution of grain boundaries if you give them enough time and enough mobility. So the mere fact that the grain does not want to exist in small grains, but that they want to grow in order to reduce the amount of grain boundaries. And if you basically just take a textbook coarsening approach, give them a little bit of variations, you end up with this kind of behavior, and you end up with these kind of distributions for a material where the mobility of the grain boundaries, which in our case actually translates to the mobility of ions across the grain boundaries, is very low. That we end up with the stuff that we get without the additive. And if we have something with the additive, we actually end up with these large grains that look surprisingly like the grain size distribution that we get with thiourea. And for this, the mobility needs to be much higher. So of course, this is a simulation, and I know experimentalists, we like to say to simulation people, you can simulate everything if you simulate long enough. So of course, we had to check if this is true. And I think Fatima is actually in the audience right here. So they did some wonderful measurements to probe the ion mobility across the grain boundaries. What they did is they used a ball mill to mill perovskites. And what they milled is a perovskite, the methylammonium bromide perovskite and the methylammonium iodide perovskite, both with and without the additive inside. Then they mixed it and measured solid state NMR during the mixing process. And then they can basically track how the mixed phase emerges and how the single phases decrease. And doing this makes it possible to put a number to ion migration by probing the mixed phase. So seeing how the mixed phase emerges over time. And then we can basically put a fit to it, put a relatively straightforward diffusion equation here, and just put the fitting parameters to compare how fast this mixing occurs. And interestingly, for thiourea, we ended up with roughly 40 times we call it the mobility parameter, or it's just a fitting parameter K that we need in order to model this one, the mixing with thiourea than without. And now we can have a look again at the grain boundary simulation that we had. So if we go from here to somewhere around down here, we would roughly need a factor of 30. And we're coming from grain sizes of maybe 120, going to average grain sizes of roughly 700, which is, I'm not sure, no, I didn't put the distribution here. We would have to go back for this, but this fits surprisingly well to the distribution and grain sizes that we have. So we ended up with basically discarding nucleation as the root cause for grain size, but that we have the grain coarsening, and apparently the ion mobility across the grain boundary is what makes it happen. So of course, now we would ask, why is it happening? This was also the reason why I was asking where the tin fluoride is sitting, because we asked ourselves the same question, of course. And the first thing that we did is Fourier transparent infrared spectroscopy, just to have an idea of where it bonds to. And it seems like, on the first glance, it seems like that we have at least some coordination of the thiourea to the light. So we did this together with Christian and Anael from EPFL. And this looked like we have it at the grain boundary coordinated to the lead. Then we went on and had a little bit of an had a little bit of an XPS measurement and looked at the chemical shifts. And indeed, the chemical shifts of the lead 5D also shifted if we expose the surface to thiourea. So we are pretty sure that the thiourea is sitting on the surface. And another thing that we investigated now again with Fatme and Helen is that we wanted to have a look what the thiourea is actually doing if we increase the temperature. And interestingly, while it sits at the grain boundary during room temperature, so you have to imagine that in the moment when we spin coat the perovskite, the thiourea is still competing somewhat with the solvent. Then we put it on a hot plate, and the solvent goes away. Then we cool it down again. Then we can measure actually. So this is the part where we can measure infrared spectroscopy, or when we can measure XPS. So this is the case that the thiourea at room temperature is actually coordinated to the lead. And then if you have increase in temperature in solid state NMR, you can see that the thiourea actually regains mobility. So if you then increase the temperature, the thiourea can move. And then we went over to Xijing Wu and Shuxia Tao, figuring out what the heck could this thiourea do there. And it turns out that the thiourea is actually an ion shuttle. So it seems to be that the thiourea is able to just coordinate to both, so the lead and the iodine, shuffle the iodine over there, and thereby increase the ion mobility in our material. So an increase of ion mobility at higher temperatures gives us big grains. So final question, how general is this? Of course, you probably have asked yourself the same question. You probably never worked with thiourea. Maybe you use methyl ammonium chloride or urea or one of the others. And obviously you ask yourself, okay, this is important for me. And we did two things. We did other perovskite, other additives, and we even tried post-treatment and used our approach to try to explain all of them. So first of all, what I showed you is actually methyl ammonium lead iodide. I forgot this in the beginning. So this is methyl ammonium lead iodide with thiourea. This is like the GWAX data. So it looks like I already told you. If we go from thiourea to urea, we actually have almost the same kind of behavior. So it's also an ionic shuttle. But DFT tells us that the adsorption energy of urea is stronger. So urea has a lower chance of shuttling the ions. And having a look at the grains at the end and also having a look at the GWAX, we see the same effect. It also comes with the annealing, but it's a bit slower. It's a bit less large in terms of grains. And finally, we also tested the same with formaldinium cesium lead iodide. And yeah, basically we have of course, we do not have an alpha phase in the beginning. So basically we had to wait for the hot plate, but also there, when we put it on the hot plate, we see one of them orienting, one of them forming large grains the moment when it reaches the hot plate. Finally, other perovskites, other additives. Now we're talking about post-processing. One thing that we did is, if we have a perovskite and if we can reform it with additives, we can just spin coat it on top, right? And it actually works. So you can just dissolve the thiourea in isopropanol, spin coat it on top, put it on a hot plate, get large grains. And the trend follows perfectly what we just learned in DFT. So methyl ammonium chloride does less mobility, urea is the next, then thiourea. A next technique that you can actually use this approach for, or this coarsening, is the hot pressing. There is basically you can use temperature just to increase the mobility. And to get roughly the same grain sizes for methyl ammonium chloride, we need to hot press at roughly 100 degrees. For getting the same stuff as urea, we have to hot press at 130 degrees. And to get the same grain size as with thiourea, we had to hot press at 150 degrees. So another hint that it actually doesn't really matter how you increase the mobility across the grain boundary as long as you do. Yeah, exactly. This is against the order that we had around here. So thiourea, urea, and methyl ammonium chloride. We did the solid state measurement again and had a look at the methyl ammonium chloride as another extreme. Unsurprisingly, we got exactly the same that we expected. So with thiourea, we got a factor in 40 in terms of mobility, while methammonium chloride gave me a factor of 2, or gave us a factor of 2. And actually, the easiest way to check if this works for other additives is just spin coat them as an additive and spin coat them on top, and then put it on a hot plate. And yeah, surprise, surprise, ammonium thiocyanate, methylammonium cyanate, methylammonium thiocyanate all behave exactly the same. Everything else, we were not able to dissolve in something that does not hurt the perovskites. So these are the ones that we chose then in the end. But I would actually guess if you are able to evaporate one of these others on top, you will get exactly the same results. So what did we do? We probed the precursors and the complexes. We can basically probe them very nicely. And the problem is that the causal connection for the additives in the lead complexes were basically not existing. The in situ investigations then told us that we have basically the reaction dynamics is roughly the same with and without additives. And during the nucleation and during the perovskite formation, and just the annealing step is very, very important. And this is basically the part when we discarded the retarded nucleation hypothesis and eventually came up with the explanation that apparently, at least for the halides, or at least the iodine containing lead perovskites, I would say like this, which are most important for all the solar cells, we have grain coarsening that is mediated by the ion mobility. We did phase field modulations, they matched. We did XPS, DFT, NMR, everything matched together. So we are actually quite sure that eventually ion mobility is what makes our grains big. And as far as we could see, it seems to be pretty generalizability. So with this, I want to thank a huge amount of crazy good scientists and a crazy good group that we're working with. And yeah, well, obviously for funding and your attention.